Hello, my wonderful students. I could not find a video with someone doing this handout, so you're stuck with Mrs. Chalk. Here we go. Non-proportional relationships. So, Fit Life Gym charges customers for each month of membership, as shown in the table below. Okay. Let's look at what this is going to look like on a graph. So if we were to graph this, let me put my little pin here. And of course, I love using the color red. You know me. I go 0, 10. So I put a dot right there. See if we can get that to make a bigger dot. Okay, 130. Oops. Let me turn that off. Okay, 130. And then 2, here's my points I'm using, guys. 0, 10, 0, 10, 130, 250. So I go 2 all the way up to 50. And then I go 370. Okay, so first thing, sketch a graph. So here's my graph. Ooh, that's not a very good graph, but there it is. Is the relationship between the number of the months and the total cost proportional? No. And why is it no? Let me erase this. It doesn't go through 0, 0. No, 0, 0. And see how it doesn't go through 0, 0? And these are not proportional. So if I put 30 over 1, because we always put the y on top, remember y over x, 30 over 1 does not equal 50 over 2. So today we're going to talk about non-proportional relationships, okay? A relationship is non-proportional if the ratio between the two quantities is not constant. It's not constant, meaning it's not proportional, okay? The ratio of, let's look at this table down here. The ratio of y over x is not constant, does not contain the point 0, 0, but instead, when x is 0, y is a non-zero constant. Okay, so when x is 0, y is something else. So I could look at this table, and the minute I see this right here, I know it's non-proportional. What about this one? If I'm looking at a graph, the line will not pass through the origin. Remember that word? The line will not pass through the origin, which is 0, 0. See, doesn't pass through here. And instead, the graph will cross the y-axis as a point known as the, here's a new word for you, y-intercept. Intercept. That's just where the line crosses the y-axis. The y-intercept is where the line crosses the y-axis. Okay, so let's go on down. The table shows the cost in dollars of jumping at Terrific Trampolines. Y in relation to the hours of jumping, okay, which is X. So this is my hours of jumping. And then this is my cost. Okay, this is my X, this is my Y. Notice my cost goes up by 2's. So if I'm at 0, I start at 6. So just to walk in the place without even 1 hour of jumping, it's going to cost me $6. Then when I jump for 1 hour, it costs 8. When I jump for 2 hours, it costs 10. And when I jump for 3 hours, it costs 12. Now I can see here what the rate of change is. And we're going to talk more about the rate of change in just a second. Let me show it to you on this one too. This table shows the relationship between X and Y. So we go 0, 1. So 0, 1, 1, 4, 2, 7, 2, 7, way up here. And then we go 3, right here, all the way up to 10. Okay, so now we're asked, can you determine the rate of change in questions 1 and 2? We actually can. And how we do this is, well, let's look at this here. First of all, if I don't jump any hours, I pay $6. But then if I jump 1 hour, I pay $8. So what's the difference there? What's the difference between $6 and $8? Well, $2. My rate of change, the rate of change is the change in Y over the change in X. So I see here that I jumped up 2. So I put the Y on top. And I jumped up here 1. So my rate of change is 2. Look at that. There's another way you can find rate of change, and it's called rise over run. Remember, rise is the Y, run is the X. Okay, rise over run. So here we see if I go up from this point to this point, I'm going up 1, 2, 3. How many did I go up? 1, 2, 3. So that's my rise. My run is how many over from this point to this point. I went over 1. So my run is 1. So that means my rate of change is 3. And we're going to talk more and more about that. Right now, we're just looking at what makes it non-proportional and what does that mean. Okay, so we're not going to get too heavy into this part yet, the rate of change, but we will. It's coming. Okay, so let's look at this here. At a pizza place, Rashid orders a pizza and it costs $8 plus $2 per topping. Okay, so it's $8 plus $2 per topping. Complete the representation to show the relationship between the number of toppings. Well, if I get 0 toppings, it's 0, okay? But I still have $8. So my cost would be $8, okay? If I get one topping, then my cost is $2 per topping. So then I have to go 2 times 1 plus 8. So what's 2 times 1? Well, 2 plus 8 would give me 10. Okay, if I go 2 toppings, it's $2 per topping. So I'm going to go 2 times 2 toppings, right? Plus 8. So now I have 8 plus 4. 2 times 2 is 4 plus 8. So that's 8, 9, 10, 11, 12. There we go. If I have 3 toppings, it's going to be 2 times 3. This is my X, you guys. This is my Y. We're going to talk more about that in a second. We're going to see how it unfolds. So 2 times 3 is 6 plus 8 is 14. And then if I decide on 4 toppings, I'm going to go 2 times 4, which is 8, plus my $8 for my pizza. So it comes to 16. Okay. So now I'm going to graph that. And this is sort of what that graph looks like. Well, not sort of. This is what it looks like. 0 toppings. I still pay $8. Oops. What happened? It went off. Okay, 0 toppings. I still pay $8 for the pizza. So there we are. 2 toppings. I'm now going to pay $10 for the pizza. 3 toppings. Just kidding. We didn't even do 1 topping. 1 topping. Oh, I messed up. Okay, let's try this again. Don't you guys hate when I mess up? I hate when I mess up. Okay, one topping. This was one topping. One topping, I'm going to pay 10. There we go. Two toppings, I'm going to pay 12. Three toppings, I'm going to pay 14. And four toppings, I'm going to pay 16. There's my equation. Okay. So now when I write there, or there's my graph. When I write the equation, my y equals 2 times whatever x is. That's what I did. 2 times whatever x is, but I started on 8. That's what my equation looks like. Let's break that down just a little bit more in our notes. What is the initial value? That's when y is 0. It's $8. Where do you see the initial value in each, when you look at the table? Where do we see it? We see it when x equals 0. Okay, that's the initial value when x equals 0. That's in the table. And then on the graph, we see it when it's on the y-axis. On the y-axis. What is the rate of change? How much did we go up each time? Well, $2. $2 was our rate of change. We didn't go up $2 each time. We multiplied by $2 each time. That's the rate of change. Where do you see the rate of change in the equation? Well, we see it right here. It's in the coefficient. Coefficient. Okay. Again, we're going to talk about this more. Just take it at face value for right now. We're just learning. Okay. Mr. Teen asked his students to write an equation to represent the relationship shown in this graph. Use the graph to complete the table and circle the name of the student whose equation is correct. So let's make this a little bit bigger because of my old eyes. Okay, when we're at 0, what number are we at? Right here. We're at 3. When we're at 1, what number are we at? Oh, it's kind of hard to see. Let's see. 1. Oh, there it is. Right there. We're at 5. When we're at 2, what number are we at? Right here. So it'll be 7. And when we're at 3, here's my 3. See, 3. Then we're at 9. Okay. Now, if we go back, so let me bring this down again, to what we used in logic here. Our initial value is going to be, so go right here is what I'm looking at. Our initial value was when x is 0. So this is going to be our initial value. And if we looked back here, that initial value 8 was at the end of the equation. See right here? See where I'm poking? So if we were to have this equation, we want the 3 to be at the end. Which of these has the 3 at the end? Well, this one doesn't. This one doesn't. This one doesn't. This one does. Look, the 3 is at the end, the y-intercept, where it crosses the y, where x is 0 is at the end. So that's our answer. Okay, we can do the same on this table. When it is 0 on the x, here is what we're looking for the last value. So this one makes this easy. We got it. That has to go here because see how we have a 3 here and we have a 3 here? So that matches this right here. Now, how are we going to know which one it is? Well, you can plug and play. Let's see. If we make x 1, so that's 0.5 times 1. Let's look at that. 0.5 times 1 and then plus 6. Will we get 10? No. We'll get 8.5. So that means this one goes here and this one goes here. Okay, that's it for today's notes. You either have a worksheet you can work on or an IXL that you can do. So it's not too bad today. I will talk to you later.